character matrix. I've specifically done it so that you don't have to think about any real life example, although if you remember in the lecture, we did that pretty simple one with the tuna and what else was on that?
Leopard.
The leopard and all of that. So that we're now taking it a step farther. I'm just saying I want you to concentrate on just the differences in a sort of abstract way or similarities in an abstract way. So I'm just numbering the characters 1 through 9, taxa 0. The 0 or this O is the out group, right? And then these are the ones that we're going to be looking for relationships between. Right? We're going to estimate those relationships. So the first thing that you always do is you always want to identify those apomorphies. Which characters are apomorphies, which character or derived, which characters are ancestral or plesiomoorphies. So how you define that is through this very important group right here, the out group. Okay? So here, whatever this character was, this is the ancestral state. So what I always do helps me sort of visually is I say, okay, here's the out group, here's the character, it's a 0, so everything that's a 1 is a apomorphy. And this is shared, this 1 is shared, so this now we have then identified this as a synapomorphy. So basically what that's saying is character 1 is evidence that A, B, C, D, E, and F are all more closely related to each other than any of them are to the out group. Okay? So then I do it with the second one. It's a 0, right? So what's the synapomorphy? Where would I circle? What would I circle?
C and D.
Yeah, so C and D, whatever that character is, share something, and that piece of evidence suggests that C and D are more closely related to each other, right? Next one, just do the same thing. Here now. This one, character 4, is suggesting C, D, and F are more closely related to each other. 5 would be here and here. 6 would be these two. 7 would be just this one. That one's not shared, so that's that kind of character that we call an ought apomorphy because it's not shared. It's derived, it's different from the ancestor, but it's not shared. Now in 8, what's happening here in 8? What's our ancestral character state?
Is 1.
Now it's 1, so now we have to look at whatever is different, right? So that one we circled the 0s, and this one we circled the 1s. Okay, so that's the first step. Identify all those derived character states. Now what I like to do is I like to say, okay, let's look at character 1 and let's translate this from a character matrix into a grouping, because what we're going to see is all of these different groupings can be nested. And the phylogenetic tree is just a graphical representation of that nesting. And so what I'll do is I'll say, okay, character 1, let's say, okay, character 1 over here, 2, 3, let's see, let me give you enough room, 4, 5, 6, 7, 8, and 9 down here. And then underneath this is saying character 1 suggests what is a group?
A, B, C, D, E, F.
Yep, so I just go A, B, C, D, E, F. Okay, now character 2 suggests which one?
C and D.
C and D, okay, good. 3?
B, C, D, E, F.
B, C, D, E, F. Okay, 4?
C, D, F.
C, D, F. All right, 5?
Is B,
B and E. Right. So B and E. 6?
E, and F.
6 is E and F. 7?
Only A.
So only A. So now I already know that's an odd apomorphy, right? So it's not going to tell us anything about relationships, but that's okay. And then 8 is
B, E, and F. Wait, is B, oh, never mind.
B and E.
It's looking at 9.
B and E. And then 9 is which one?
C, D, and F.
C, D, and F. Okay, so C, D, and F. So now we have, this is all of our evidence. And so now what you want to do is you're then going to construct this nested hierarchy, right? Some people start from the largest and go to the smallest. My PhD mentor did it that way. I like to go from the shortest, from the smallest to the largest, right? And so here I can start with character 2. And I say, okay, this is suggesting that C and D are more closely related to each other than anybody else. So I look at that and I say, okay, let's look at the other characters and see if there's contrary information. Is this contrary information?
No.
No, because C and D can be nested in there, right? C, is that contrary information? No. Is that? No. Is that? No.
Doesn't matter.
Is that? No, not either way. Is that? No, that's not contrary to that. No. Is that? No, because it can be nested. If there was something that said C and E here, that would be contrary information, and then we'd have to assess where is there more information. Which grouping do the data support more strongly?
So same thing if you were to have D and E, you would have contrary.
Yeah, or D and E, yeah. And we'll get to some of that. We'll get to a bunch of that actually. But here, okay, so C and D, no contrary information. So I just go over here and I go, okay, C and D, and I just group them together, little V, right? Then I kind of draw a line through that. So there's C and D, okay? Now let's look at another one, B and E, okay? So here, character 5 suggests B and E are more closely related to each other than anybody else. But here, 6 says it's E and F. So that is contrary information, right? So these are contrary things. So which one do we go with? We look for which one has more support or less contrary information, right? So E and F, B and E, does that suggest anything about those? No, that's not contrary information. B and F or B and E, is that contrary information? No. How about this one?
No.
Yes, that's contrary information because E is not included in here. So E is saying, this one is saying E and F are more closely related. That would be contrary to what it's saying there. Okay, this one, neither. This one, this is now more support. So now we have two characters that suggest B and E. Two characters in support, one in contrary. How about this one? This one's also in contrary. So we're gonna go with B and E, all right? Now that identifies that, I'll identify that with an asterisk because that is telling me that one is the homoplasy. That's where you had convergent evolution happen. All right? So B and E here, group it together. Okay. B and E, cross there, cross that, and that one's, I put an asterisk by it, so that says we don't have to worry about that one anymore.
And you just chose B and E because there was less.
It's a smaller grouping. I just went to the next
and
one.
there's less saying that it's not
Yeah,
right. Less
there's
to the
two
contrary.
characters that are supporting it, and does that one, is that one contrary to B and E? No. Is that one contrary to B and E? No, there's two supporting it, there's 0 against it. This one has 1 supporting it, and 1, 2, 3, 4 against it.
Wouldn't you say 1 is also supporting it though, or
It's
not
just yeah.
necessarily-
I mean, yeah. It's not it's not really supporting that particular grouping, right? But it's not contrary.
Okay.
Okay. So now we go to the next bigger one. What's the next bigger one? Let's look at 4, C, D, and F. So here's one character that supports C, D, and F. Here's another character that supports C, D, and F. This one is the one that you remember that was that one doesn't. But is there any other contrary information? No. So here with C, D, and F, just put the F here, and to show this, we now group that one together. So that's taking care of that one, that's taking care of that one. So now the next bigger one is this one, right? This one we kind of ignore for now because it's a odd apomorphy. Next biggest one is 3. So at 3 we have B, C, D, and F. And so how do we show that grouping? Here's our C, F, D, and here's B, E. All we do is come here and bring that down to there. That takes care of that one. Now the next one, A, which one do we need? A in there now? B, C, D, E, F. And we put A in here. Bring that down. That takes care of that one. And then we have our outgroup. Now, so there's our tree. We've now constructed our tree. Now we go back through and say, okay, let's plot the characters on there because that'll be a nice test for us, because everywhere you have this bifurcation, this node, you have to have a synapomorphy that supports it. And then also we can do this thing called calculate that tree length. So where A is hit, so character 1 gets plotted here, right? That means everything above it has that character. Character 2 gets plotted here. Character 3, B, C, D, E, F is plotted here. 4, C, D, F gets plotted here. 5, B, E gets plotted there.
And F though, right? There was no F on them.
No, that's 6. So 6, E and F, this homoplasy, this gets plotted here and here. That's where there's been that conversion evolution. That's that homoplasy, or an analogous character. 7, we'll still plot it on here just so we can be consistent. 7 is there. 8, B and E, that's here. And then 9, C, D, F, that one's here. Now to count up the tree length, what do we do? How do we get the tree length?
It's all those numbers on.
Yeah, it's everywhere we've had this evolutionary event. So what we do is we just count them all. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Tree length equals 10.